Okay, hi everybody. This is the replacement lecture for Chapter 4 for Material Science. We're going to do a couple calculations that we didn't get a chance to in class. Okay, to begin, we want to derive the formula for the fraction of vacancies in a um, metal or a crystalline solid. And if you recall what that is, the fraction of vacancies is given by this Boltzmann factor. It's an exponential of minus the energy of formation of the vacancy times kT, where this is the temperature in Kelvin, and this is the Boltzmann constant, which connects temperature and energy. Okay, so we did work out the numbers for these things. We plugged in typical values for the temperature and Boltzmann constant and stuff like that. So that part we've seen, but I wanted to derive where this comes from. It's based on two principles. First is the thermodynamic definition of temperature. So if you take a class on thermodynamics, you will define temperature in the following way. Um, the temperature basically tells you the relationship between entropy and energy. So it's a derivative. It's the derivative of energy with respect to entropy. Sometimes this isn't really a well-defined thing to do, and I think the more proper way to define it is in terms of the entropy function, which usually is a well-defined function of energy, and you divide it with the inverse like that. So this is the usual kind of definition, but we will not be too rigorous. And so we will just say that basically temperature tells you about relationships between small changes in energy versus small changes in entropy. So S is entropy and E is energy. There's a kind of funny analogy um, between these things. That you can make. So energy you can think of as kind of money, and entropy you can think of as happiness. I'm not sure who thought of this analogy first. It might have been Daniel Schroeder. He wrote a kind of famous textbook called Thermal Physics. I think it's probably from that. But in any case, so entropy is like happiness, energy is like money, and T is sort of like greed. So the idea is that according to the second law, systems tend to try to maximize happiness. So they try to increase this. So systems. So how do they do that? Well, you can do that by like giving the systems energy. So depositing a little packet of money or energy into the system. And the temperature basically tells you how much happiness you gain for a certain amount of energy. So we can sort of rearrange this, I guess, so that it's a ds is equal to dE over T, kind of roughly. So it basically says that if the temperature is high, so if T is large, then it takes a lot of energy to increase the entropy by, a certain amount. So the larger T is, the larger your greed is, the more money basically it takes to raise your happiness by the same amount. So if T of large takes more delta E to get a certain delta S. And vice versa, if the temperature is really low, then even for a small change in energy, you can gain a lot of entropy. It basically tells you the nature of systems at low and high temperature. At low temperatures, even small amounts of energy will distort the system and make it disordered. Whereas at high temperature, everything's already so sort of noisy and random that even dumping in a lot of energy is not going to change the entropy very much. So that's kind of the idea. So for T small, uh, small delta E increases S a lot. And for T big, it's already very hot. You need large energy input um, to increase the entropy. So that's the basic idea. But we're going to mostly use this definition. And the other important thing is the definition of entropy. So entropy, so that's the other important concept is the statistical definition of entropy. This is probably due to Boltzmann. So I think this equation I'm about to write is, I believe, engraved on his tombstone. So it's S is equal to the Boltzmann constant times the log of, this is a capital omega. This is a natural log, so it's the inverse of the exponential function. And this thing is a number. It's a number of states consistent with a certain macro state. That's easiest to demonstrate probably for a gas. So if you have a gas and, the gas is at, the gas has an overall energy corresponding to sort of the kinetic motion of the little um, gas molecules in there. So it's got maybe like a fixed energy or something. Then you can imagine that all gases with sort of the same fixed energy, the same kinetic energy, they're kind of equivalent. So I could draw like three gas particles right here. If I look at the gas again and the particles moved somewhere, so there's still three of them, but they're in some other locations and maybe their velocities are pointing in somewhat different directions. Those are still the same macroscopic state. So for a fixed sort of energy and number of particles in here it's like n is equal to 3. Basically, omega corresponds to all the different ways you can arrange the atoms in there with their different velocities and positions, such that you still have the same fixed energy and the same number of gas particles. So omega counts all these states. And there's countless number of them. I mean, like a truly large number for when you have like a bunch of particles in a gas. So that's what it does. It's like given a certain macroscopic state, like at a certain energy, a certain total number of particles, then this omega counts the number of possible microscopic states. So maybe a better way to kind of make this more precise, it's the number of microscopic, where you specify everything about the system It's the number of those microscopic states corresponding to a certain macroscopic state. Okay, so what does it have to do with vacancies? So we imagine, and so these are the two things that will need this sort of definition of entropy and this definition of temperature. There is, I guess, one more thing that we'll need, which is energy conservation. So um, energy is conserved. So those are the three things. One, two, three. Okay. So what's the setup then? You imagine a system that maybe consists of a small portion of the lattice, maybe just like you have some kind of solid, and you consider basically one or maybe just a couple unit cells, maybe that are filled with atoms, say like this, some solid. And you imagine the solid lives in an environment that is held at a fixed temperature T. So that could be like the rest of the solid, and you could be looking at a small piece of the solid, something like that. But there's some environment, um, and it's at temperature T. So what happens? What we are going to be interested in calculating is the probability that you find your solid in a certain microscopic state, and we're going to call that X vector. This is a microscopic state uh, of the solid, meaning this small piece of the solid like here. So it could be like the probability of finding like 4 occupied lattice sites versus 3 occupied lattice sites, some kind of microscopic configuration. So the idea is the probability of finding such a state has to be uh, dependent on the various environments that are consistent with having that particular microscopic state of the solid. So if you see 4 solid atoms in here, there must be lots and lots of different ways in which the environment could be arranged that is still consistent with the solid having sort of 4 occupied lattice locations, right? So there's lots and lots of configurations, which we'll call sort of omega sub R for actually, or maybe omega sub E is better, E for environment. Sometimes it's R because R means reservoir, and the environment is like a temperature reservoir, but this is sigma E. I mean, omega E, that's the number of microstates of the environment. So what the probability has to be is the number of microstates of the environment consistent with the microstate um, of the solid. So it's given that the solid is in this particular microscopic state, this is the number of environments that are consistent with that. So this is number of environments or environment microstates consistent with uh, the solid in state X. And then, of course, you have to divide by something. So each of these are equally likely, each of the environment um, microstates consistent with that solid being in state X. But we divide by the total number of possibilities for the environment. So this is like the total. So that would mean this probability distribution is, of course, properly normalized, meaning that all the probabilities sum to 1. So if you sum over all the possible states of your solid, you will get that this is just sum over all the possible states of the environment. And that should just be the total number. So that's how you know what the total number is. It's just the sum of all these numbers for all the different possibilities for the solid. So okay, so that's a probability distribution. Now we're going to um, consider two different states. So consider two states, X and X prime. And let's say they have two different energies. So um, EX and EX prime. So now what do we have? We know that how do we get from say state X to state X prime? So if our initial state is X and our final state is X prime, say that's like four occupied locations or something like that for our solid. And just as an example, and then the final state is maybe where one of the atoms is vacant. It's like missing. So there's going to be some change in energy associated with this kind of transition from this state to the next. So um, some amount of energy must go in and out of the system in order to uh, initiate this transition. So there must be some energy that goes into the solid, and we call that sort of delta E. Now, that energy must come from the environment. Either energy is going into the solid from the environment or out of the solid into the environment. So the overall energy is conserved. So the change in energy of the system, we'll call this the system or the solid, plus the change in energy from the reservoir, or I guess we're going to call it the environment, little e, that has to sum to zero because any energy we get that's put into the system has to be compensated by energy leaving the environment, which we're denoting in red here. So, okay. So now let's do the calculation of the probability ratio between the final and the initial state. That, according to our top formula here, is so I guess, by the way, there's sort of a fourth assumption, but it's sort of implicit in all of thermodynamics, is that all the microscopic states are sort of equally likely to appear. And that's it's kind of a logical assumption because there's nothing biasing the microscopic states. So if we look at a gas, say, right, at a fixed energy and number of particles, there's nothing really that's going to tell us that the gas particles have to be in any particular corner of the system. We could find them anywhere. So any particular microscopic configuration is equally likely, just because it's sort of like the Occam's razor type argument. It's sort of the simplest um, logical assumption that if you have no other constraints other than like total energy and total number of particles, then any state is going to be equally likely. And if it's not equally likely, then we can always pick another macroscopic variable in order to make sure that all of them are equally likely. It's a subtle point, but hopefully it sort of makes some intuitive sense. Okay, so the ratio of probabilities, now both of them will have this total number of environmental states, so those will cancel out. And what you get is just the number of environment states that are consistent with the solid being in state X prime over the number of environment states with the system in state X. And now we do some tricks with exponentials and logs. So we are going to these are just numbers, like positive numbers. So we can exponentiate them and and do a natural log. These are inverses of each other, so we're allowed to do this kind of thing because it's a positive number. It's non-zero also. So we can always take the log of it and exponentiate it, and that just cancels out. And we do the same thing on the bottom. And now what we do is, hopefully you sort of remember that when you divide two exponentials, that's the same as subtracting the exponents. Okay, now we do one more trick. There's a couple sort of funny tricks. We multiply and divide the top and bottom by the Boltzmann constant. So inside the exponential, I'm going to write the exponential as exp. That's a way of just, it's a nice notation. I think you've seen before, but so e to the x is the same as exp to the x. So I don't have to write like, so it's less confusing what's actually inside the exponent. So you kind of know that everything in these brackets will be inside the exponent. Okay, so you multiply the top and bottom by Boltzmann constant. So you get this. All over KB. And now you recognize that this thing is the entropy of the environment consistent with state x prime of the solid. And this is the entropy um, of the environment consistent with state x. So that makes things kind of simpler. So this is the entropy of the environment at consistent with state x prime minus the entropy of the environment consistent with state x all over the Boltzmann factor. Okay, now we have to use the definition of the temperature. So the change in entropy for the environment is in going when the solid transitions from one state to another is just this guy, right? It's the final entropy, final minus the initial. And according to our formula for temperature, it has to be related to the change in energy of the environment because change in entropy has to be change in energy over the temperature. And the environment has a well-defined temperature, so this is actually the change in energy of the environment divided by the temperature. But we know where, by the way, the change in the energy of the environment is just like the energy of the environment, given that the system is in state x prime, minus the energy of the environment, given the system is in state x. So, okay, the very last step is just recognizing that energy is conserved. So the change in energy of the environment is negative change in energy of the system. Right? So this is just minus delta E over T, where this is now for the system. Okay, so now we plug in and we get that the ratio of probabilities is exponential minus the delta E of the system over now KBT, which just says that if there's a transition between two states, X prime and X, and if that takes some energy, some positive amount of energy, ES, then the likelihood of that happening is suppressed exponentially. The more energy it takes to make the transition, the less likely it is. So that's basically how it works. And now you can see how you can use this to calculate the fraction of vacancies because, say, X prime is like a vacancy and X is no vacancy. So then, uh, in that case, and if we're just considering our solid as just a single lattice location, so the state X would just be a single lattice location with an occupied atom versus unoccupied. Then the change in energy is just the energy of formation of a single vacancy. And so the probability of X prime just must be the fraction of vacancies. And the probability of no vacancies just must be 1 minus the fraction of vacancies. So then you can see that fraction of vacancies over 1 minus fraction of vacancies is equal to E to the minus QV over KT, which is the formula that we use in the book. Of course, this sort of assumes that this part assumes that all atoms are equivalent, so all lattice locations are sort of the same. Okay, so that was one thing. And then the other thing I wanted to discuss is just that the book spends a lot of time talking about compositions of atoms. And so it's kind of good to talk about those. So they talk about like three different kinds. So there's like CI, CI prime, and CI double prime. So this is for alloy compositions. Okay. And so the first kind is in terms of the mass percent. So that one is probably the most commonly used. If you have an alloy, say like copper and nickel, you specify what percent of the weight of the alloy is one thing or another. So like Cooper nickel we had, that was one alloy we considered. I think we mentioned compositions like 75-25. So 75% copper, 25 nickel, that's by weight. So what you do for that is you say that the composition, say, of copper is, 75%. That's what it would be by weight. Now that's different from the atomic percentage because that corresponds to the number of atoms you have. Um, so copper and nickel have slightly different atomic masses, so their percentage by weight is not quite the same as the percentage by atom. So I like to work in fractions, so I think I'll show you the conversion with fractions instead, as opposed to percentages. I think it's annoying to have to multiply by 100, but you can always go back and forth because you can get your final answer in a fraction and multiply by 100 to get the percent. So this one, the double prime, is the last kind of thing that the book talks about. That's composition that gives you a mass per volume. So I'll talk about that too. But let's talk about first converting between weight percent to um, atomic percent. So what do you do? So if you have, say, the fraction of some component one in terms of the weight, that means you have like the mass of component one over the sum of the components. And let's say there's just two, like copper and nickel. How do you get the number of atoms? Well, you need to convert the mass to a number of atoms. So you do that by taking the mass and dividing by the atomic weight. So this is the atomic weight. Um, And then for the other one, you have M1 over A1 plus M2 over A2. And the trick here is that you can actually divide the top and bottom by just the sum of the weights, or you can just take the top and bottom and divide by 1 over M1 plus M2 and the bottom by 1 over M1 plus M2. And that leaves you with M1 divided by the sum of M1 plus M2. That's just the same as F1. Um, oh, by the way, so I shouldn't put an arrow, I shouldn't put an equals. This is like I'm going to convert to percentage by atom, which is in the book denoted with a prime. That's F1 prime. So it's the fraction of component one by atom as opposed by weight. So you take all the masses and you divide by the atomic weights. And then if you divide the top and bottom here by the sum of the masses, you get the fraction now in terms of the weights up top and on bottom. And you just get this kind of formula where what do you do is to get the fraction by atom, you take the fraction by weight and divide by the atomic mass. Now, the book like tabulates all these formulas, but I don't think it's worthwhile to memorize all these. It's better to just know how to derive them. Um, I think. I mean, you could get a cheat sheet that sort of records them, but I don't think it's that worthwhile. So let's try it for copper. So it's for copper. Um, in like the 75-25 uh, alloy. So, all right, what's the fraction? Let's see what the atomic fraction of copper is. So the fraction by weight is 0.75. And we have to divide by the atomic mass of copper. So I do have that tabulated. Um, that's 63.55. Um, The units all cancel because we have a fraction. So you basically get a 1 over AMU upstairs and a 1 over AMU downstairs. So the units all cancel, so you don't have to worry about that. So this is atomic weight of copper. And then the other one is 0.25 of nickel, and nickel has an atomic weight of 58.69. Okay, now we have to jump to a calculator. I don't have this calculated, so just bear with me while I plug it into my computer calculator. Okay, I get 0.735. 0.73. Let me double check that last digit. 735, yeah. So you see the actual amount of copper is a little less because copper is a little bit heavier than nickel. So if you have 75-25 by weight, um, it's actually a little bit more balanced in terms of the actual atoms. You have 73.5% atoms copper, and then the rest is nickel. So that's how you convert from um, F1, the fraction by weight, to F1 prime, which is by atom. Okay, so that's one thing. And of course, you can go back and forth. There's nothing preventing you from doing the same thing, but backwards. So say you have like F1 prime, which is the number of atoms of type 1. So this is number of atoms now. of some component one over, N1 plus N2. You can even do multiple components. Maybe there's like a triple alloy or three different components. If you want to know then how do you get the percent by weight? Well, that's easy. You know that it must be the mass of component one divided by the mass of component one plus the mass of component two plus the mass of component three. But you can use the atomic weight um, to convert to between masses and numbers. So if you have the mass, then you can just divide by the atomic weight. So these are the atomic weights. And sorry, oh, you can, sorry, not divide, but you take the number and multiply by oops, you take the number and multiply by the atomic weight. So you have N1 times A1. That gives you the mass, right? That gives you M1. If you have the atomic weight times the number of atoms. Okay, and then here you have N1A1 plus N2A2 plus N3A3. And then you do the same kind of trick where you multiply and divide the top and bottom by the sum of all the numbers. So you do N1, A1, and then this entire numerator you multiply by the sum of all three. And on the bottom, you do the same thing, you know. Everything on the bottom here gets divided by the sum. That's really the only trick here to get all these conversion factors, because then we can recognize that this combination of N1 divided by the sum, that's just the fraction by number, the F1 prime. So this just becomes A1 F1. Here it's A1 F1 plus A2 F2 plus A3 F3. So going the other way, you multiply the fractions by the atomic weights. I think oh, I should gotta put primes. Sorry. These are the primed ones. These are the fractions by number. Okay. Uh, so if I go back, so if this is my conversion formula for going from fractions by number of atoms to fraction by weights, then you can see it's sort of the opposite of the one where you go the other way, right? Because there you divide it by the atomic weights instead. But hopefully it makes sense. You should just be able to reproduce these conversion formulas yourself. I don't think it's that bad to do, but you could also just write them down or something. I think the book spends a little too long tabulating all these things when you just have to be careful with the logic and, the main trick is just the multiplying and dividing by the sum of the masses or the numbers of atoms. That lets you go, convert back to fractions so that you can write things as sums of constants that you know times fractions that you've already presumably calculated or know. Okay. Uh, let's do one more example that's sort of more interesting, and that's modern bronze. So modern bronze, like if you get some bronze material, it's typically going to be 88% copper and 12% tin. So these would be your F1 for copper. This is by weight. Again, it's by weight, these percentages. So by weight, it's F1 is 0.88 and F2 is 0.12. So, okay, let's convert that to percent by atom because that's more relevant to um, the physics of the material is knowing like what fraction of the atoms are actually copper or tin. So if we want to do the fraction, say, of tin by atom, the prime means by atom, right? Then this is going to be the fraction by weight, and we want to divide by the atomic weight of tin, and then this is going to be F1 over A1 plus F2 over A2. So it's the same kind of example, I guess, but um, it'll be a slightly more interesting result because copper and tin actually have very different atomic masses. So um, F2 is 0.12 over the atomic mass of tin is 118.7. And then this is 0.88 over 63.55 and 0.12 over 118.7. If we plug that in, we get a fraction by atom, which is going to be quite interesting and different from we had before. So tin is very heavy. So it's going to reduce that fraction when we do things by atom. So that's 0.068. So that's actually 6.8% as opposed to 12% by weight. So it's 12% by weight and you know, almost half that by atom. So far fewer tin atoms than you would expect sort of by weight. Okay, so the other one to know is this third one, which is the mass per unit volume. So the way that works, let's do it, say, for bronze, F1 or maybe F2, I guess, double prime. It's the mass of the second component or whatever component you're looking at. So the mass of it over the volume of the material, which is the volume of component one plus the volume of component two. How do you get the volume? Well, you need the densities. So if you have the mass of component two, then you get the volumes by taking the mass of the component and dividing by the density. So you need to know the density of each component. And then M2 over rho 2. So I need to look up the density of both tin and um, copper. So I know the atomic weights. This is the atomic weight of tin, and this one's the atomic weight of copper. But the densities I don't know, so I have to look that up. You bear with me. Let's see. So density of copper looks like it's 8.96. Um, grams per cubic centimeter. And the, let's see, the density of tin. 7.31 grams per centimeter. Kind of surprising. So this will depend on like the lattice structure and stuff like that. I would have thought tin is sort of more dense, but I guess that makes sense. It is sort of soft, white metal. I don't know. I find that a little bit surprising, I guess, but I guess the lattice must be more loosely packed, I guess, for the tin case. But okay, let's figure out what this is. And this will have units of grams per cubic centimeter. Usually you want to convert that to kilograms per cubic meter, but we can do that after. So, okay, M2 is, we need one more step. So we don't know these M2s, but we know the fractions by weight. So what we do is, again, we divide the top and bottom by the sum of all the masses, and hopefully you see the pattern here. You just get F2 up top, and then on bottom you have F1 over rho 1 plus F2 over rho 2. So those are the fractions by weight. So F2 double prime, this is the kilograms of tin per volume of material. Or we'll convert it to kilograms, it'll be grams per centimeter at first. So for tin, it's 0 point, what are we doing here? 12 for tin. And then it's 0.88 for the copper divided by the density of copper, which is 8.96. And then F2 is 0.12. And we divide by 7.31. These are in the denominator, so the overall unit goes into, it's the denominator of the denominator, so overall the units in the numerator, it's grams per cubic centimeter, whatever number we get. And if we want to convert to kilograms, we know there's 1,000 grams in 1 kilogram. And then we need the meters converted also. We need 3 factors of that. There's 10 to the 2 centimeters in 1 meter. So the overall factor here is 10 to the 3. Because we have 10 to the 3 in the bottom, but 10 to the 6 at the top. So, okay, let's plug in. And what we get is, again, I need my calculator, 0.12, 0.88 over 6. Okay, I get 1.05 grams per cubic centimeter, or 1.05 times 10 to the 3 kilograms per cubic meter. And it's actually useful to know this because it's like a concentration. So it's that's helpful to have as a measure. So if you have like a minority component, like tin inside copper, then if you want to know how it moves around, it's useful to have its concentration, in this case in kilograms per unit volume. We can do other stuff as well, like calculate the average density of the alloy. So if we think about what the average density should be for a material, that's the overall mass, right? It's the mass of component 1 plus the mass of component 2 over the volume of component 1 plus the volume of component 2. That should be like an estimate of, you know, the density of the material. Now, if you want to now you want to write this in terms of mass fractions. So again, we have to use the density of the individual components. And you see you'll have, to get the volumes, you need to take the mass of each component and divide by the density. And then again, we do the trick where we multiply the top and bottom by the sum of all the masses to get just the fractions. So this is F1 plus F2 over F1 over rho 1 plus F2 over rho 2. But we also recognize that these sum to 1 because they're fractions of just the 2 components that we have. So they just add up to 1. So you get that the average density is just the fraction by weight of component 1 over its density plus the fraction of component 2 over its density. So kind of a fun little formula. It's a little bizarre because you don't think that you would have densities in the denominator like this, but it all works out because the physics, or the meaning of average density should just be the sum of the masses over the sum of the volumes. So then it sort of makes more sense. I won't plug in the numbers for this one, but hopefully you get the right, sort of the idea of it. You can also do something like calculate the average atomic mass of the material. That's very easy to calculate in terms of the atomic fractions, because if you know what fraction of the material is a certain atom, then you know how it contributes to the average. So if you have two components, then if you know the fraction of the atoms that are component one, you just multiply that by the atomic weight of component one, and you add that like that. Now, if you don't know these atomic fractions, you can, of course, get them from the conversion formula we had before, which was these guys. You can take the fractions by weight and divide by the atomic masses. So if we were to do that, we could just do F1 over A1. This is actually times A1 divided by uh, F1 over A1 plus F2 over A2. This is just rewriting F1 prime as, well, this part. This is the conversion formula. And then the other part is, let's see, F2 over A2 times A2 over, same thing, F1 over A1 plus F2 over A2. So some stuff cancels, right? We have some cancellations here. The A1s cancel, the A2s cancel. And these are actually, they have the same denominator. So this reduces kind of nicely to F1 plus F2 in the numerator, which is going to sum to 1 because they're fractions. That's what I like fractions more than percentages, because fractions add up to 1, and that's much easier to kind of deal with than percentages that add up to 100. I know it might seem sort of be that's sort of obvious, but I do not like the book for spending so much time on percentages when it's easier to just convert to fractions. And then once you're all done, you can always go back and multiply by 100 if you want, but don't really think it's all that necessary. People understand that, a fraction can mean a percent. Okay, so F1 plus F2 is just 1 because the fractions add up to 1 for like a binary alloy. And you have this funky kind of thing at the bottom where it's the by weight fractions divided by the atomic weights. And that gives you the, that's again, that's the average atomic weight of the alloy. Also, it can be expressed this way more simply in terms of the fractions by atom. And finally, again, we have the average row. Now, okay, we can also do the average row maybe by number. If we really want, it will introduce the atomic weights. Do I want to do that? I mean, you can see what happens. You can take these F1s and these F2s and replace them with the fractions by number by using the conversion we had before, which is like this one. So we can replace F1 and F2 with just the by number fractions, but multiplied by their respective atomic masses. So I'm not going to do that. I think it's a little tedious, but I think you should work through these conversions yourselves and sort of make sure you understand where the formulas come from. And I really think you don't really need a cheat sheet for this. You should just be able to reason through it step by step yourselves just by using the logic of what it means to have something as a fraction by weight, which means you're dividing the masses like this, versus a fraction by atom, which means you're dividing the number of atoms. And the conversion between those, the numbers and the masses and the atoms is, of course, the atomic weight. And then if you, in addition, need to have volumes involved, which involves the way the atoms are packed, then you need the density because the density incorporates all that in it. So if you need volumes, you need the density of the components. So it is important to note that all this assumes that sort of everything is well mixed and all of this sort of material is homogeneous, that the two metals mix with each other, and we can just sort of do everything on average. So that's why we can convert between all these things and add them together just by their fraction. We don't have to worry about maybe like this patch of material is like particularly dense in one kind of metal versus another patch is less of that metal. It's assuming everything is well mixed. So maybe just to summarize, again, we have the three different kinds of fraction by weight, by number of atoms, and then this one means just, or a component I. It's the fraction of component I, or double prime, which was the mass of component I divided by the volume of the material. And to go between masses and volumes, you need the density, rho. To go between numbers of a component and the mass of the component, and you need the atomic weights. And we put an I here. So to go between the volume of component I and the mass of component I, uh, so this is for any component I of an alloy. You have this kind of thing. And then hopefully just using logic, you can figure out the conversion formulas without having to look them up in a table. Yeah, the main idea is you have these three different kinds to go between masses and volumes. You use the density of that component, like the pure metal, to go between numbers of atoms, and the masses, you use the atomic weights because the atomic weights tells you the mass per atom. So hopefully that makes sense. And hopefully, we worked in a couple examples to sort of show you how it works. Just involves calculating a whole bunch of fractions inside a big fraction. But hopefully, it's not too bad. Like the worst it can get is sort of like this, where you have a fraction on top and then you sum up two fractions on the bottom. So it's not the worst. And most alloys will be binary alloys. You have two different kinds of metals mixed together. At most, maybe you have three. Okay, so I think I'll leave it there. So thank you.